And this is a session on remote monitoring. We got three great speakers today. Before they start, I would just emphasize that within the wind energy program, and I think all of AEA, we strongly encourage people to invest the small margin of cost that goes into these remote monitoring capabilities so that during the design phase, you're actually dealing with accurate data on what your power system's doing, what your resources, how they're behaving, and then once you build a project, that infrastructure is already there, and the ability to go in and post-construction and see how the system is truly operating and to work collaboratively with the people in the villages to troubleshoot issues or just dig in deeper of what's happening in their systems. It's so beneficial. You get a higher availability on your equipment. You get more fuel savings on these projects. So we can't emphasize enough how important it is to put this in because the benefit to your systems are so much greater. So our first speaker here is Dan Reitz, and he's with Alaska Native Tribal Health Consortium. He has a BS in Civil Engineering from South Dakota School of Mines and an MS in Environmental Engineering from Virginia Tech. And he's an Alaska professional engineer and been involved with Alaska sanitation system design, construction, and operations for more than 26 years. And almost all of that has been out in rural Alaska enhancing their infrastructure. So, Dan, we'll let you go.
Okay, thank you. Is there a laser pointer with the
laser pointer right here?
Okay.
And then you just advance slide from the
okay, laser
right,
pointer's the middle?
Middle, right. And then the little right arrow will be advance your slide.
Okay. Okay, good morning. Thanks for having me. My title of this presentation is Low-Cost Alternative to Remote Monitoring. I'll get into it a little bit. ANTHC builds water sewer systems and clinics all over the state of Alaska. We have an opportunity, to get involved with the energy projects, and that's why I'm at this conference. But there's another side thing we're doing, and that's this remote monitoring. So I'll kind of go over how we're doing this. This is my one energy slide of the presentation. But energy in our in the water plants that are out in rural Alaska, as Arctic, subarctic areas. Energy is pretty much one of the biggest costs and variable costs, something that can be controlled. So that's why we are in the energy or looking at energy problems. So remote monitoring. There's been a huge investment in the past 15 years by the state and federal government in the infrastructure in Alaska. We have some freeze-ups. If a system freezes up, we could lose potentially, tens of millions of dollars of that infrastructure. So this remote monitoring effort was more to try to find something that could help, say, remote maintenance workers or our ARUC operations people help identify impending problems before they actually happen. And then with the Renewable Energy Fund, and we're doing energy audits and finding there's very little data on things like fuel consumption and usage, so we need to do some energy monitoring. So we weren't looking at a full SCADA system and being able to control things, just we wanted to be able to look in at it. It didn't need to be real time, but not continuous. So EPA funded this effort, and they gave us a challenge of trying to come up with a system that we could put all the monitoring points in and pretty much the entire system, labor, equipment, for $8,000 or less per site. And at that time, we were talking more of at $100,000. So they pretty well dictated that it's going to be a very low cost kind of thing that you don't go in and with a large construction crew or a lot of engineering. It's just focusing on preventing catastrophic failure. So this is what we ended up with, kind of on the backs of Alaska Housing Finance Corporation. They kind of had started it using this technology and this brand of Monet sensors. But what we have is we have different sensors. If you want to think of it, this bottom half is all in a water treatment plant. So within the water treatment plant, we have different sensors, and then we have a gateway. So the sensors are battery powered. They talk to the gateway. Then the next question was, how can we get a really inexpensive internet connection, because internet's fairly expensive in villages, and just for this effort, what can we do? So we came up with this CloudGate. It's a cell phone modem, and with GCI has a $10 a month data plan. So that's essentially our internet connection, is with a $10 a month data plan. It's not a continuous, it's not high speed. These things download once every 10 minutes or whatever you set the heartbeat at. It feeds to here, and then every so often this releases it, and then it's generally an edge network or an E-network. So anyway, goes to the cell phone tower in the village, and from there then it goes to the internet. And I'll show you a bit more about that now. This is that's the CloudGate. You put the little GCI card in that, and then you got $10 a month internet connection. And that's the gateway. That's about this big, and it just sits in the building, kind of like a wireless router. Here's some of the sensors. What we were trying to do is, to the degree we could, we wanted to be able to send a technician out and install these without having to do a lot of hard wiring, plumbing, cutting pipes, that kind of thing. So what you see here is 3 of what we're trying. This is an ultrasonic flow meter. It was a $120 unit out of, can only buy it on eBay, but it's been working pretty good, but it's kind of a pain to set up. Temperature probes, they were right. They're one of the least expensive pieces of per point monitoring. They were about $50 per point for those. Here's a pressure sensor. You just replace the pressure gauge and you hook the Monet pressure sensor up. So that's kind of the technology. Now with the Monet, once you put the sensors in, these are the different locations we have them. You take each sensor and then you can pop it open, and at that point you can see what it's been reading. But it's also, I don't have the more slides, but this is also the place where you set it up. You tell it if you want an alarm when it gets too cold. An alarm, you can put in a number of email addresses or text. You can send text messages, or water system's cold. Hey, so we haven't quite got to the alarm, setting the alarm up. This is still a work in progress. But so you set it up on the Monet website, and now I'm going to show you, hopefully. The internet was kind of slow this morning. A live demo. Is that it? Okay. So this is from our Ambler water plant, and these. Oops. So you can see we have a problem with the water storage tank temperature, but this tells you how long ago it took the readings and then what the readings are. Now for energy, this is what we set up. This is kind of our prototype for reporting to AEA. We had a heat recovery project in there that was funded by AEA, and so we need to be able to report. So what you would do once you're on this site, you would click the hyperlink there, and which they're going to try to do, or we're going to go to the next page, and you would see what's going on with the heat recovery in BTUs or gallons per hour, or we can totalize it. It's all pretty simple. So you can see that somewhere around September 22nd, they probably, in fact, last night I overlaid it. We can put multiple graphs on there from this point, but I overlaid it with the airport temperatures, and you could see right about here it was getting below freezing, so they must have decided kick it on for the season and then be able to watch it. So Because the internet's so slow, I wanted to do, oh yeah, we were going to do we're going to just show you a couple of the, yeah, the internet is so slow here that, so you could also see up there that there was the ability to download this data in Excel. We're often asked for data from our water plants, and as we get these online, we're going to just refer people to this and say, go get it, download it in Excel, whatever data you want. If it's there, it's there to be used. So I'll go to the, so all these work the same. You can plot multiple at the same time. So I'm going to, okay, I'll go on to my next slide. If we could flip back to the PowerPoint. Okay. There's Scott Waterman in the back. A lot of this was made possible by him and the Last Housing Finance who set this thing up. This is, we're playing with this dashboard. I'm not real excited about it yet, but it's kind of a work in progress. So I'm going to zoom through this. This was my backup in case the live demo didn't work. What we're finding also is instead of catastrophic failure, as we get these online and people start looking at them, they look at these and go, what the heck is going on? And this was at the, oops, I zoomed back too much. Okay. This is the Chivac water plant. It's the tank, the water storage tank. And we were going, okay, it's at 16 feet. All of a sudden it zooms up to 20 and immediately comes back down. Well, what was happening was pressure sensor was on the line going to the tank. So as soon as the pump kicked on to fill the tank, the pressure sensor would think the tank's full and turn off. So this just, it helped us find a problem that we didn't really even know existed. So we went and put a new pressure sensor in out in the tank where the pump wouldn't affect it, and this was what it looked like after that. So it's helping us identify things we didn't even know we had a problem with. And so that's kind of cool. And every day somebody's going, hey, did you see this? And it's like, like I say, what the heck's going on? So we haven't hit the $8,000 a site. We're closer to $15,000, but there's still development costs. We haven't got everything working the way we want to yet. The CloudGate thing was probably one of the biggest deals. To, you know, a $10 a month internet connection was great. Flow rates, that's important to us to know the water's moving out through the system in town, and that it's really desirable, but that is the hardest point to set up. They're most expensive, and we're looking at alternatives, just watching whether the circ pumps are on or off, or potentially a flow switch, watching temperature of water going out, coming back. We may not be doing the flow rates much more because it just takes so much tinkering to get them to work right. Pressure gauges, we had problems with those, and Monet's been really good to work with. When we tell them they have a problem, they go out and they'll re-engineer their sensor, and they're going to build us some custom sensors. So we want run times for boilers as a surrogate to watch fuel oil usage, and that would be a slap-on inductive sensor that would just see when the boiler kicks on and kicks off, and from that we can infer fuel usage. In the future, there are quite a bit of other non-Monet sensors out there. Our website is not a Monet specific. We're getting data like from the National Weather Service, from the airport. We can accept the data from a number of different places. Now we need to try to accept data from some other sensors in other buildings. We're working on the runtime stick-on. We're doing some frozen ground monitoring. That just came online this week, where we're watching the effects of a kind of a special project for freeze back. We're going to improve the websites, and probably the biggest hurdle to date is who's going to watch this. Fear being, we set up this monitoring. The assumption is somebody's looking at it. And if something does freeze up in the future, it's, well, weren't you monitoring that? No, we haven't defined. So we've kind of working on the technology, but haven't got some of the people responsibilities worked out. Who's going to, mainly, who's going to maintain it and who's going to be responsible for watching it over the long term. So I think with that, I'm done. I hope I kept it within my time. So.
Thanks, Dan. We can open up the floor to 1 or 2 questions for right now, then we'll have each of the speakers go do the same thing, and then at the end we'll kind of have some more general panel questions too. So any specific questions for Dan on his presentation? Yes, Scott.
Fuel flow. Any progress on good fuel flow?
The question is any good progress on fuel flow? Okay.
We're working with a consultant named Alan Mitchell. He's developing a new sensor. It's the runtime sensor, and I think we deployed that now in I want to say one of our most recent, and we're watching going to watch boiler runtimes. One of our other folks in our ARUC are going to actually install some fuel flow meters that are going to have some pulse outputs that hopefully we can then hook them on it to the pulse output, because that's really the holy grail, is knowing how much fuel are you really using, because there's really poor records out there. Generally, we have to go off of delivery records. You know, how much oil did they get in what year, and how many years did it last, and who was using off of it. It's pretty sketchy. So yeah, that's one we're working on. But the first thing is going to be the run times as a way of watching hours that the boiler's running. So yeah.
You say that we're monitoring, so who's watching those right now? Is that ARUC, or
the technicians and engineers that are right now working to develop it are watching it but long term, that's the problem. Now the ARUC is watching it for real, and in fact, a couple of weeks after we got one set up this winter, we prevented a freeze up, and they were really happy. They were seeing the water tank get really low in one of the villages that I won't mention, but the last time that happened and it froze up, it was about a $300,000 bill. And this year they saw the water tank getting low and was able to head it off. So we want to do our ARUC ones because we know those are going to be watched. EPA's intent is that the remote maintenance workers will become responsible for monitoring it, looking at it every day, analyzing the trending. But right now, that's a problem.
All right, thank you, Dan. Our next speaker is Dan Rogers. Dan grew up in what's now South Anchorage, back when it wasn't, and it was a different place. It was basically woods out there, some trails, and you could get into all sorts of fun and trouble out there. Really, it was true Alaska back then. And then after high school, he attended the University of Alaska, getting an electrical engineering degree, both a BS and a master's, and as well as a BS in physics. And he worked as a controls engineer for a local electric utility during that period. And then he had the opportunity to go down and work for a startup in Pullman, Washington, and also pursue a PhD in electrical engineering down at Washington State University, and fortuitously also met his wife there. And after coming back to the Anchorage area, he's been involved in some startups, the key of which is he's a co-founder of Electric Power Systems, which now has more than 200 employees, offices in Anchorage and Juneau, Redmond, Olympia, and Vancouver, Washington, and Lawrence, Kansas. And they provide design and construction services for the electric utilities, oil, water, wastewater, and other industries. So, Dan, take it away.
Yeah, I either have to get some of that stuff off my Facebook page or defriend Rich, because that's just way too much information. I didn't remember half of that. Oh, what do we got here? We got a, okay, we'll go with this. I apparently gave these guys the wrong slideshow. Oh, that's right. Yeah, sorry. Funny story, my mom, who obviously is, I'm old, my mom's older, she used to sit there and point the control for the garage door opener up at the top of the car like this, you know, even though the sensor was behind her or something. So I guess I inherited that gene. This actually isn't the Alaska Wind Diesel Conference, but this is a similar slideshow. Apparently I downloaded the wrong one, so we'll go with this. But it's okay, because it's the same thing. We got to deal with remote monitoring. I'm really not doing that. Let's see if I can go back here. I am trying to go back one. If you tell me it's too hard to go back one, I'll go forward. So the issue is, in a lot of the systems we work with up here with remote monitoring and SCADA and control, the reason we do it, it's kind of fun and it's cool and all that stuff, but the reason we do it is there's a pretty strong economic driver in doing it when we start integrating these systems to a high level. So a number of our clients and friends out there for many years have gone from purely diesel systems to diesel with hydro, diesel with wind, and now we're doing things with, I'm going to put this down until I need it, diesel with controllable loads. So there's in order to try to extract as much economic benefit from the fuel as we can, especially in rural Alaska, we're ending up putting a lot more devices in the system, and thus we're having to control, and we have to control them precisely, because if we don't control them precisely, precisely and correctly, we either won't get the optimal, see this? No hands. We either won't get the optimal usage of the fuel, or in some cases, if we really do it wrong, we may end up burning more fuel than we would have if we hadn't had, for instance, a controllable load in there, if we don't control the load correctly. So am I doing that, or are you? Okay. I'm feeling really powerful here, but no control at all. So the idea behind the remote monitoring and the SCADA systems that we put in, again, are to try to take these integrated resources that the utilities, primarily the utilities in this conversation, but also water and wastewater systems we do as well, and try to optimize the system from a cost perspective. I'm going to put both hands up here so you can see I'm not doing it. So do you want me to take over? You got it? Okay, we're good now? Okay, so. No. Yep, just that one right there. Maybe we got a dead background. We've still got. So can you forward a couple slides? I'll tell you when to stop from back there. Can you do it from back there or not? The pictures are nice, but if we don't get there, we can just talk about this too. Yeah, the remote monitoring is a lot easier than running a projector, apparently. No, that's okay. I'm sorry. You know. Okay, so we've got new batteries. Still not moving forward. Okay. It's just slow?
No, it's moving on just the PowerPoint.
Okay. So I guess I'll continue to talk while we get slides moving here. So again, we're trying to optimize the use of primarily the BTUs and the fuel that you have out there. Now try it. Two clicks. 3 clicks. I'll quit clicking now because I know it's going to go crazy if I don't stop. So kind of what we've done, and since we're not working here, we'll kind of go and talk about a couple couple aspects of it here. So Rich mentioned that I grew up in South Anchorage. Actually, my folks homesteaded back there back in the 50s, and I grew up on a homestead back there. And what I remember, even big city Anchorage, right, for Alaska, what I remember as a kid is we always had to go, if we wanted something special, it came from Seattle, right? And in the next couple decades, Anchorage got to be big enough and got to have some expertise in it. And then the rest of the state kind of leaned on Anchorage and Fairbanks and Juneau regionally. One of the things we're doing right now, and the remote monitoring, just yell at me when you think I should try it again. Okay. That was 1 click, 2 clicks, and now I'll stop again. So one of the things the remote monitoring allows us to do is it helps us to work with our clients. And so first I'll talk about some of the regional hubs. So Kotzebue, Nome, we're talking about northwestern Alaska at least. Both COTS and Nome have put in remote monitoring SCADA systems, and they've actually developed, so these are monitoring. It's different in the communities because the energy resources are different. COTS currently has got wind and diesel that we monitor and work with, and then the heat recovery system as well. So this allows their operators to see, kind of as Dan showed, but in a little more graphical presentation, see what's going on with regard to the wind system and see what's going on with regard to the diesel system. From a control standpoint, it allows us to optimize the wind. So it's a pretty simple concept and fairly common sense. There's not a lot of higher math here. What we're trying to do is, and what you guys are all trying to do, is burn the minimum amount of diesel, which if you assume no conservation in this whole thing, what you want to do is you want to use the most wind that you can. So the way we do that, and I think Kotzebue is a great example of it, is the wind comes up and we have, there's no throttle on the wind, just like there's no throttle on the runner of the river hydro. So we let the wind come up and we start backing the diesel units down until we get to a point on the diesel unit that's online that we can't go any lower. Try it now. Negative. Oh, something happened. That was you, though, I bet, wasn't it? It's just going crazy? Okay, let's do it this way. Thank you, Rich. So yeah, this is what we're talking about here. So the conceptual dispatch, or the way we dispatch the units, the way we run the units, is we want to maximize the non-firm renewable resources that we've got. So in the case of wind diesel, that means we want the control system, the remote monitoring system, wants to go ahead and say, let the wind go. Let's get as much wind out of this system as we can. And then we regulate with the firm resources, because we've got throttles on diesel units, right? So, and then the third piece that jumps in here is we can then regulate or modify the load with controllable loads and energy storage. And we'll talk a little bit about that. Next slide. Let's go ahead and skip this one. Kodiak's a really cool story, but I think the Buckland COTS discussion really lends itself to this group a lot more. So I started talking about, we'll go back when I was trying to song and dance here while things weren't working. Talked about in the old days, we all had to go to Seattle for expertise, and then we all go to Anchorage, Fairbanks, or Juneau for expertise. What we're trying to do is develop this expertise regionally now in the hub communities in particular. So Buckland, COTS, and Deering is a really nice example of kind of what's, I think, going on there. Kotzebue has been running a system that is built to maximize wind and have remote monitoring, and so the operators can use that automatically in most cases and manually when they have to maximize their wind resource, thus to minimize the diesel fuel burned. So how long has it been, Brad? 10 years you guys have been doing this? With the remote monitoring SCADA. So they've got 10 years with pretty much the same operators, and they know how to do this now. So now we come in and the Northwest Arctic Borough's got a couple projects up there, Buckland being the first one, and then Deering following on behind that, where they're going to have the same types of goals, where they're putting in winds, or Buckland happens to be putting in the Northwind 100s, as does Deering. And then the idea is going to be the same, to try to maximize the wind, minimize the diesel generation. And just to talk about it, I started talking about that too. Sorry for the scattered nature of this, but I think technology got us again. And that's funny, we were talking about how technology was going to bite us on this one. But at any rate, so what we do on trying to maximize the wind, basically what we do is we let the wind go, we get as much energy as we can out of it, and we back the diesels down while regulating frequency until we get to what we call a minimum diesel set point. And just for argument's sake, on a 450 kW unit, that might be 200 kW, it might be 225, it might be 250. That's a parameter that the operators, we'll give them some input on that, but with experience, they can modify that. So now if you get down to 250 on your diesel, and you've still got more wind resource there, you can do one or two things. You can curtail load, you can curtail the wind generation, or if you're fortunate enough or have planned well enough that you've got a smaller unit, maybe you've got a 250 kW unit that you can run down to 100 kW, you go ahead and flop units, put the smaller unit on, and then run that as the wind comes up, you run the diesel down to your minimum diesel set point. Now let's say that you have a lot of installed wind capacity, and let's say the wind is still coming up and you're down at 100 kW on your smallest unit, and that's your minimum diesel set point. That's when we go ahead and start using the controllable loads to try to do other things that are beneficial to the community. And what those are effectively doing, right, is displacing heating oil. So whether you're putting it in a community pool, water storage, circulation system, whatever you're doing, that controllable load, assuming it's and both Buckland and Diesel are water heating loads. You go ahead and start taking over another job that was previously done by fuel-fired boilers. So the nice thing about that is it's an understandable and it's a really efficient process. Now, as we talk about this, you've got Kotzebue doing this sort of thing and has been doing it for quite a while now. They've got experience with it. If COTS runs into problems, they can call us up, and Brad has got my phone number, as do all his operators, and have all our technicians' numbers. They call us up and say, hey, something's not looking quite right here. Can you take a look at it? This is a remote monitoring aspect, is we can go in and we can look and see with their permission what they're looking at and work together with their operators. It's not like we're coming in as experts, because we have a perspective of the system. The operators have an awesome perspective of the nuts and bolts and how their system works. They've got the best information of any of us on how that system works. So you get on the phone, you're looking at the data, they're looking at the data, and generally you come up with a solution. So that's the way the models worked with Kotzebue with regard to remote monitoring. Our hope as we move forward, and this has been KEA and Northwest Arctic Borough have had these discussions. We're now with Buckland, hopefully Deering, and some other communities. Now KEA has had that 10 years of expertise. They've developed some expertise in these systems. Now Buckland's going to be, once the system gets up and running within the next year, Buckland will have a problem, or have maybe not even a problem. They'll just see something that's curious, and they'll call up Claude and ask the operator at Kotzebue, hey, have you guys seen this before? And now COTS becomes kind of that regional hub for experience and expertise. We can still get into it if they together need it. But the nice thing now is we're forming these cooperatives of expertise regionally. And I don't know, Brad, you can speak to this too. I don't know how much COTS and NOM have worked together on these things, but certainly NOM is in a similar position too, although Kotzebue probably has more wind experience than NOM, and they've got different machines. But from a controls perspective and looking at data perspective, there's really some nice islands of kind of expertise developing out there. So it's kind of been one way the remote monitoring has helped, really help develop the usage of a lot of these technologies, and really has made the concept of higher penetration wind systems or run-of-the-river hydro systems more realizable. So, and one thing I think Dan talked about that I'll mention too, we'll put these systems in with, we talk about what points we want to monitor, and and they're all kind of the standard things, right? You want to look at fuel, you want to look at kilowatt hours, you want to look at temperatures on water systems, you know, all the stuff that, you know, we can all sit around in a room and kind of come up with, and we've got ideas why we want that. But the really interesting thing about this is that you give these things to the operators, and they'll come up with something that we never thought about. You know, they've got this data, they've got the ability to, in a limited way, massage it and look at trends and look at what's going on, and they'll say, hey, you know, I've got you know, on a bigger diesel, I've got a turbo inlet and I've got a outlet temperature, and look at what my differential's doing. Or I'll look at a pressure, you know, on one end of my fuel system, and I'll look at it on the other end of the system, and there's a filter bank in between those two things. And they'll go, wow, over the last 12 months, you know, instead of looking at today's data, they'll go, you know, the pressure difference seems really high. So they'll take the outlet and subtract it from the inlet, and they'll go, that's kind of weird. I don't think it was that much pressure. And then they'll look over the last year, and they'll see their differential pressure rising across their filters. And guess what? You got a filter that's clogging up, or that's, you know, needs to be maintenance. So it's amazing to us, the ingenuity and the ability of guys that work with this stuff every day. They're really a lot smarter than we are, because they figure out, we kind of give them the basic tool set that covers, you know, 75% of what we know they'll need, and then they go and use the data most of the time to extend this and develop new capabilities and new operating paradigms where they can actually make their systems operate better. So real quick, I'll show you some, since this thing this is the whole Buckland discussion that we just had. These are some of the GNOME screens, just to give you a real quick. And when we talk about remote monitoring and SCADA, when we work with clients like COTS or GNOME or anybody else, and there's different security protocols for each of the utilities. Some guys say, yeah, we've got multiple levels of passwords on it, we're comfortable with that. Some of them will say, no, we got to have real hard security, so we're going to unplug internet connection to this thing. And so various levels of security, but at one point or another, they're all remotely accessible, you know, within the rules that the utility develops. But when we look at it, we see the same things they do. And it really makes it nice for talking through with the operator what's going on. And, you know, just for whatever reason, I'm not sure what was going on here, but they've got their emergency generator now on. He's just basically heating up one transformer. There's probably more going on. This looks like, given the, and you guys can't see all this because of the way it's displayed, but this was probably not a very pleasant time in the operator's life, because this looks like they're coming back from an outage. You know, Dan kind of hit on devices. There's all sorts of things we monitor. We can monitor relays, can monitor meters. You know, you can interface with devices like, well, there's another meter, but you can use protocol converters to talk with other devices that are out there. GNOME also monitors their whole water system. There's some building stuff going on up there we can do. So it's, hey, did you guys notice this is working kind of now? But at any rate, so this is the kinds of things we see when we, you know, when we build a system like this. So my time is up, and that's okay. But sorry for the kind of roughness of the presentation. But any questions? Did I give you enough to ask questions about? So the question is, what kind of tools does SCADA provide for the aggregation of data and then the analysis of that data? You know, it depends. It depends on how you provide the system. I mean, and Jason I think will touch on this a little bit here when he comes up. From an operational standpoint, which is really primarily what we deal with, there's a tool we use we strongly recommend. It's a commercial product called Canary Labs. It's not horrendously expensive. It's got an incredible ability to store huge amounts of data. Brad's had his system for 10 years. Cordova, CEC, Clay's not in here because I think he's giving a presentation right now, but their system's been up and going for probably 13, 14 years. And we've never had to do anything hardware-wise other than buy, you know, the biggest disk that they had at the time, and that, you know, it went from 500 megs to however many, you know, gigs we're buying now. But Canary's really good at compression. It's also very, very good at doing things like zooming in and out of windows, which from an operator's perspective is really what they need. We can also export it CSV and things like that for manipulation outside of there, but you know, or even for doing some things that are a little more esoteric than that. But from an operational perspective, it's just it's a commercial data management tool that we generally provide when we do a system like that. And Brad can probably comment on it more than anybody else. It's cool. I mean, it's not expensive, and it's pretty efficient, and the operators can use it.
They love it. It's really been a wonderful troubleshooting tool for us to be able to have it very lab back. You know, say, geez, we had an outage or something, what happened? They can go back and they can press that time, expand it, they can look at the voltages, the ampere gun system, they can look at which engines we're on. They go back and that's really refined their ability to troubleshoot the whole system. So then some they can say, well, that's coming through a feeder into the system that could be, and we had a couple this summer with construction, trucks running into our poles and making them do things and knock the system off because we got his alarm. But it's been a great tool for the operator for sure to be able to do that, take a picture of what's going on at that point, and then go back and think about it. Sometimes we call the electrical engineer in to see what's going on, or sometimes man people are there and say, what happened? You see anything here?
You know, an example, the other Dan, the first Dan, brought up too, it reminded me of one. You know, that example where you had a pressure sensor on a input to the tank. We had one, and it was up at Nome on the water system, and we were spilling water in a tank, and it was because of a bad VFD tune, a variable frequency drive that was running a pump. And you could see it, you know, the operators were the ones that caught it. They pull it up and they go, hey, this isn't right, you know, look at what's going on here. And you know, we went up and retuned the VFDs, which is a complete, you know, had nothing to do with SCADA. It was a standalone VFD module for the PID for the variable frequency drive. And you know, then you see the tank, you know, stop filling, empty, and then you know we're keeping it at whatever 80%, minimum 80% full, maximum of 97% or something like that. And you know, you can actually see that stuff, and the operators are the ones catching this stuff. So I'll repeat that. Brad's got his hand to his ear, and most of these questions may be his. I'll give you a couple anecdotal pieces. So the question was, do the SCADA system install when you build a new power plant, or do it as a retrofit, or do it as a part of a new wind install? And then the other one is, what are relative costs, and what else was in there? Oh, O&M costs, yeah. Does it increase the cost of, yeah, so most of the work we do, to be real honest with you, is probably split 50-50 between retrofitting older plants, and then, I don't want to say 50-50, maybe 70-30. Most of our work is retrofitting old plants. And then when you get a new project, like a wind project, you know, now you've got, and Nome's good history because, you know, we did Nome, we did the water system, we did a couple of the units. And then Banner Creek came in, the first project, and then the EWTs came in. And because then all of a sudden they went from being a no-wind system to a pretty high levels of wind system, then it's still in process work. It became really important to be able to control the diesel so that we could maximize and optimize the wind. So the wind drives a lot of these projects. You know, it's kind of a nice to have for a while, and man, it'd be really cool if we could do that. And then all of a sudden you get wind in the system, and it's like, oh, we really have to do that in order to make our wind economical, you know, make it work. So I'd say that's kind of the split. You know, the problem is the cost of, I can give you a couple examples, and maybe Brad can too. The cost, you have to ask the question slightly differently, you know, because an equivalent would be, what's the cost of an electric generator? Well, it depends on whether you're getting a 20 kW for your house, or you're building Bradley Lake again. So the cost is all over the map. We did switchgear when we did you guys, right? The first time, Brad. And So the switchgear was, yell at me if I'm saying something stupid here, but I'm thinking the switchgear was $300,000 or $400,000, and that wasn't necessarily a SCADA-driven thing. It just, we happened to be doing it at the same time. And I think the whole, what was the SCADA piece? About that, 300 grand for COTS?
Yeah, it was kind of more than that. We put the two projects together. We were replacing 1950 breakers and putting in a lot of newer equipment. So we updated the whole power plant when we did the SCADA system. So it was 1.2 times everything.
So now, and this is a, this is a big, pretty good sized system too, and this is a piece of big metal-clad 12 kV switchgear, so that was rolled in there. One thing I will tell you, and ask Clay Copeland, if you guys don't know him, is Cordova Electric Cooperative is around here. Clay was one of the early adopters of this, and his story is similar to the wind diesel thing, because at the time he had run of the river hydro. He's still got run of the river hydro, but he's got a little bit more storage in his run of the river. And Clay's claim, and again, fact check me on this one, was that his payoff on that system was somewhere around 18 months. Because it really allowed, that system is kind of like Brad's, it was really cool. It allowed us to do a lot of things there to, deflate dams and inflate dams to get a little more storage in, because they had this, if you guys haven't seen it, they've got an inflatable dam up at the Power Creek project, and then they had the old Humpback project, which ran rarely, if ever, and we managed to get that thing going and controllable from town, remotely from town. So, yeah, it's not cheap. The smaller systems are less expensive for sure, but the bigger ones like COTS, Nome, and Cordova are definitely more spendy. I'd almost hate to even throw a number at a small one without looking at it, but I'd say. You're looking at 100,000, maybe 150,000 for a 300-400 person community, and that's absolutely throwing stuff at the wall, but that's the kind of numbers. But especially if you're integrating wind, the payoff is definitely there. And Josh may have some words about that, because I think we're kind of going through that right now with Nome, aren't we, Josh? About how efficient we can get, and what tools we need to get efficient there. Sorry, I'm running away.
No, that's fine. No, I just add that it's whether you've got an existing system and you're retrofitting, it will tell you a lot about what's going on in your system, and identify opportunities for improvement in how you're operating, reducing your costs, whether it's reducing diesel or other costs. So these systems are great. And then certainly when you're looking at putting in additional generation types into your system, like wind or solar or hydro, it's much better to have real data to be able to model and design your new system around, as opposed to making a whole series of assumptions that are probably in the ballpark. But the error bars start to add up, and so we highly encourage folks to adopt these if you're in the reconnaissance or feasibility phase of a new project. Just the benefit can't be understated on these systems. So thanks, Dan. Next up, we have Jason Meyer, who is the program manager for data collection and management at Alaska Center for Energy and Power. And he has his professional expertise really spans sustainable energy and international development. He has a BS in chemical engineering from Colorado State University. Go Rams. And an MPP from the Harvard Kennedy School, and he's served as a Peace Corps volunteer in Vanuatu, which is a group of islands. It's a republic of islands about 1,000 miles due east from northern Australia, and he's worked for the State Department in Fiji and for BP in Alaska. So welcome, Jason.
Thank you. I'm a little nervous about the PowerPoint now, but it should be okay.
I got all the bad news.
Hopefully. So hi, my name's Jason, and I just wanted to touch on a program that we've developed here at UAF at the Alaska Center for Energy and Power, focusing on data management. And a lot of my presentation is going to specifically focus on the management of high-resolution data from some of these remote systems. So let's try this. All right. So the Data Collection and Management Program, our mission is to support Alaska communities, agencies, and utilities in the collection, management, and dissemination of high-quality technical energy data. And through this program, we really have a series of objectives. A couple of them are listed here. One is the facilitation of data-driven decisions, whether that's through design or analysis, as Rich mentioned, having access to real high-quality data in order to model a system or help you design a system or assess or analyze the system. Another objective is to reduce what we call data friction. So data friction being the ability for you to access a data set that you're interested in or have it available to you or collect that data. Just any of these aspects that really limit our ability to meaningfully have access to or manipulate data sets. Another somewhat selfish objective is to support robust, high-quality research. So, allowing people, whether it's at UAF, UAA, internationally, to conduct very high-quality research that's, you can submit to peer-reviewed journals and such. Another objective is cooperation, synergy, and compatibility. We really think there's a lot of areas to partner on, whether it's in support of a utility or a government entity. Just we really want to be good partners in supporting those organizations. This last objective is the communication of Alaskan expertise and experience. And through our work, we find that Alaskans are doing some amazing things. Just whether it's a wind diesel system or reliable energy in rural Alaska, and internationally, that it's really amazing what we're doing up here. And just through the use of data to be able to allow people to communicate that expertise and that experience, for us, we think is a real opportunity for people. The PowerPoint presentation available, I have a link to our program that kind of outlines all these in much detail. Just a little bit of background. Our program, we offer 3 different types of services. The first one is more on the data collection side. So this is like instrumentation, programming of controls, technical assistance. The second one is management. So what I'm really focusing on today is the management of data. So that could be processing and standardization. It could be dissemination, conducting quality assurance on data. The last one is what we call product, but this might be more specific to a project or a contract. If there's assessment needs to be done, if there's a certain type of dissemination of data that needs to be done, we can provide that. Just by way of an example, a couple of our current DC&M projects, our primary project is in support of the Alaska Energy Authority's Emerging Energy Technology Fund. So projects that are funded through that fund, we work with the recipients to develop a data collection plan and then execute that data collection plan. When you're funding an emerging tech project, you're really funding the generation of information. So our objective is to work with the project and ensure compliance with grant responsibilities, which is really just the solid collection and dissemination of data. So for instance, if any of you visited the Oceana project in Nenana on Monday, you'll notice there was a lot of computers and equipment on deck, and they're actively collecting data from that demonstration that we then receive and then work with them on submission AEA. We're developing a similar partnership for the Alaska Energy Authority Renewable Energy Fund, so working with select projects on collecting data and then allowing that data for meeting reporting requirements both on the project and then the program. There's a lot of reporting that goes on with the Renewable Energy Fund, in particular to the legislature, so ensuring that that capacity is met. And then historically, we've done similar activities on the Denali Commission Emerging Energy Technology grant. So I wanted just to kind of, again, zoom back out to the context of high-resolution data. High-resolution data being, sub-second data that we're collecting off of utility systems or power projects or what have you. As Rich and others have mentioned, as our projects are getting a lot more sophisticated with the integration of wind and storage and controls, and it's really, you need really robust data to be able to understand your system, design systems, assess systems. So high resolution data is really important, especially as our systems are getting a lot more technical and complex. It's really important for modeling. So just having real data as opposed to making just a host of assumptions that, who knows. So that's just another example of the usefulness of high resolution data. Being able to do event analysis, so really understanding cause and effect. Was it my wind system? Was it my diesel engine? What's going on in my system? That zooming into something that's sub-second really allows you to get to some of these events. And in many cases, your system might be collecting high resolution data if you have a SCADA system in place, and maybe you're just not recording it. So again, being able to, what I'll present on, manage that data could be really beneficial. There's a case study. Dan mentioned the Canary Labs. This is from Cordova. If you see Clay, he probably has a copy of this case study. It's really interesting, just through their use of Canary and having this data available for them to be able to go in and identify various maintenance issues and set points has really saved them a lot of money. So just as an example, using Canary. So the ability to manage high-resolution data at our end really begins with the resources we have at the university, primarily being our access to the Arctic Region Supercomputing Center. And this for us has just been a really powerful resource to develop this capacity. And so through the Supercomputing Center, we have several resources available to us. One is the use of Linux stations, so we can send out batch processing on many workstations, and it really, for us, speeds up processing time and just our ability to run through calculations and processing of data. We have website services, the Alaska Energy Data Gateway shown on the right, and this is a currently active website funded through the DOE UpScore program in partnership with many people, including the Institute for Social and Economic Research. This is a website that actually hosts currently data information, and for us, we're looking forward to being able to disseminate high-resolution data through this website. And again, that's hosted through the Supercomputing Center. And one of the last resources we have is storage. It's a supercomputing center, so there's lots and lots and lots and lots and lots of storage. So for us, that's been very valuable, just dealing with large data sets. This is just kind of a simplistic diagram of data workflow. So data enters ASEP through several means. One could be through a physical hard drive that you bring in through the door. Another could be transmitting data to us through like an FTP site. So for instance, Cold Climate Housing Research Center, they have a emerging tech project looking at a ground source heat pump on their property. And that project daily transmits their data to us just online, and that enters into the supercomputing center. And so once it hits ASEP, we conduct a lot of processing, quality assurance, whatever the data management needs are for that data. And it enters the supercomputing center. There's a lot of archiving that we have. That's a tape drive at the supercomputing center. But there's a lot of redundancy in archiving that can get done through the supercomputing center. And then eventually, if it's needed or certain permissions are allowable, we can disseminate that data then through the Alaska Energy Gateway. So this is, for us, really the bulk of our development work that's gone on. So using the Canary Labs example, taking raw data from, let's say GNOME, from their Canary system. So data will enter our system as, in this case, CSV file. It could be basically any raw file that we get. And just inherently, it's a large file. It could be messy, it could be clean. It's just, who knows? It's just kind of wild data that's coming in from the system to us. We'll do initial processing. It could be formatting. It could be correcting fields. It could be working with headers on that data. And we then convert it to we use MATLAB just as a current example of a processing tool. So our MATLAB processing is really where we start to process and standardize and clean up the data. So we'll convert it to SI units, and we'll ensure that timestamps are standardized across all the channels coming in, as an example. We'll conduct quality assurance. So this could be filtering, so trying to identify anomalous data through thresholding, what have you, looking at data irregularities, are there gaps, are there holes in the data, and then looking at calculated values, statistics, whatever is needed for that project or that data set. And then eventually converting it, in this case, to NetCDF data format. NetCDF is just it's a data format that allows you to package what we call metadata into your data set. So it's data about data. So you understand this is the power output of a diesel generator, and in addition, you know the make, model, you know, all the technical information you need to know about that generator. So when you receive a data set from this process, you have a data point, but in addition, you have the complete context of that data point in the system. So that's really what, in this case, NetCDF allows for. This is very difficult, processing these large data sets. So CSV files, for instance, are comma separated files. And so, you know, this could be 6030 or it could be 630. And it just depends if, you know, through whatever errors, was that comma used correctly as dividing values, or was it used to indicate magnitudes? And we see this all the time with .csv files. It is so heinous. So then you have to run very complex processing scripts on your data sets to be able to go through and analyze, you know, what are the meanings of these commas in this data set. And that can take, you know, traditionally months to do. So anyway, we've been able to really develop processes that allow us to do this in hours on very large, complex data sets. Extraneous information, so headers, there could be proprietary information about the Canary Labs system, for instance, and it just all adds size and complexity to your raw data set that comes in. So for us, being able to remove a lot of this complexity, simplify it, is a very incredibly process-intensive undertaking. Missing information. So for us, when we originally set up a database, we work with the utility or the customer to understand, okay, what are these values coming from? What's the data about this data? So what's the make and model of your instrument or your generator? What's some of the other contextual information about your project? And so we'll add that into the database as well. And then again, like time conversion, how do you handle leap years and leap seconds? And, you know, is this based on Alaska Standard Time? Where is this project? So just being able to make sure that all your data channels are standardized and they all make sense. So I just wanted to give a brief example, just kind of to indicate the magnitude of some of this data. This was a data set from GNOME, and they use Canary Labs as their historian. So we processed 2 years of data, so May 11 through October 2013. And notably, during this time period is when both the first and the second wind project came online. So this data was 1 second or less. In some cases, there were 4 samples taken every second, some case 3, some case 2. So very inconsistent, but always multiple readings per second. And again, in CSV format, we had a combination of 99 channels, and then when the final wind turbine project came on, we had 127 channels. So just as an example, one week of only 14 channels was about 400 megabytes. It was more than 3 million rows in Excel. And, you know, I could always tell when my colleague down the hall was, you know, his Excel exploded on his computer. You just, you know, the wailing that comes down the hall. But just as an example, just the size and magnitude of this data that we're dealing with. So again, just through this process that we've developed, being able to optimize and process this data, so you can get a monthly file for each channel with all project metadata associated with that file. And you know, at first, if you would have tried to do this on your laptop, it would literally take you months, and we've been able to reduce this process to hours, again, using the supercomputing center and our programming and such. Just as an example, again, going from that initial raw CSV file to a MATLAB file, it's 15 times smaller. So cleaning out things like the proprietary or canary-specific information, commas, et cetera, really can reduce your file size to a very manageable data set. So all this, I guess the point of all this is, again, to really reduce the data friction and availability, your access to this very important high-resolution data from these very interesting systems. So one thing we can do then, once we have this cleaned data, rectified data, is things like automated reporting. So your project is generating data, it comes to us, we process it, and then we can, it's fully automated, generate a report based on your needs, and that could be to meet your grant requirements. So this is what our system is producing, this is how it's producing, this is any errors that were developed. And this is a very, very powerful tool to be able to deal and monitor your data, what's going on. Are there any anomalous events happening? You can develop these reports on a weekly basis, on a monthly basis, on a quarterly basis. So this is just one example of what you can do once you've processed this data to a very usable format. This is an example of a report that we worked with Cordova on. So we have, again, a similar file type, CSV from Cordova coming to us. We process it, and then we can produce automated reports that can look at trends or analysis or errors or issues with their system, whatever it be. So that's just kind of the flexibility that this process allows you to get to. And as an example for something like the Renewable Energy Fund, if you have a Renewable Energy Fund project, having this service in place would automatically be able to report your data, whatever your reporting requirements are, to AEA or to the ICER, to the legislature, what have you. One key aspect to this is quality assurance. So being able to monitor, like, is there anything anomalous happening with my data? Are there any trends that are out of the norm that I need to be paying attention to? So this is an example from a data set we were looking at where the data was continually resetting to 0 in a certain time scale. And just doing some simple processing, we were able to understand that what points were actually erroneous to the data set. So everything highlighted in red was kind of the system was falsely indicating 0 when it shouldn't have been. And again, just through some automated processing, being able to clean your data set to a point where this is more representative of what's really going on with your system. Sorry, my time is running short. 2 points I just wanted to highlight again. So one is the data access and dissemination, and this is for, if there's a requirement of public reporting, or you're very generous and you want people to have access to your data. For us, developing this Alaska Energy Data Gateway, this portal that allows you to download these clean, rectified data sets for whatever time scale you want, for certain time points, for a certain location. That's a service that we're going to be providing. The last slide, this kind of ties in more directly to the data, the remote monitoring, but high resolution data, I mean, there's a lot of issues with collecting and transmitting it, right? I mean, internet connectivity could be very slow or expensive, as an example. There could be security concerns at your utility. You don't want an internet connection into your data. That's a common issue. There could be reliability or redundancy, concerns or requirements. So this is actually a tool that we've been working on for a couple years, and it's actively being prototyped and tested at our lab as we call it a black box data acquisition system, but basically a self-sufficient black box you can put into your remote utility, connect it to your SCADA system, and actively download high-resolution data without any internet connectivity or any other issues. So something that could collect over 200 channels, sub-second data, you can just leave it and forget it, and it can collect high-resolution data for over 2 years. So these are some of the design goals that we're working towards, and it's been very successful so far. So I just wanted to mention this. And again, there's a link here on the PowerPoint if you wanted more information with that. So with that, I'm going to wrap up so we can head towards lunch and Q&A. And here's contact information. We have many project partners working along this project. Myself and Aaron Whitney is contacts for this program. So thank you.
All right, any questions for Jason specifically, and then we'll open it up to the whole panel. Okay, questions for the panel? I know I have one or two. In fact, I'll just lead off. Can you folks kind of talk to the degree at which you think that what people should weigh the options of how much data to store remotely versus how much to transmit over the whatever internet connection may exist? Because I know there's times when you need to see high resolution data, but you can certainly affect the bandwidth at the community scale versus when you need to just transfer 10-minute data or hourly data, those kind of things. And anyone who wants to respond? He's got the most unique.
We're a very low resolution data user, so and it fit our criteria of low cost, and it's nice and slow too. But anyway, yeah, we as far as storing it, when it's important for us is sometimes there's power outages in the village or internet interruptions, and our data logger will keep like 2 weeks worth of data, and when the internet connection comes, it will download it all at once again. So,
yeah, I guess from our perspective, this offsite or redundant on-site storage of data is completely user dependent. So for a lot of the operating utilities, I mean, we're dealing with real-time stuff. I mean, the operators want to know either right now what's going on with their system or what's happened in the last, recent history. So a lot of the rural utilities we work with don't have a lot of need for, either a program of continuous backup of data. Having said that, in the Canary, and Jason had a good point, when you export from Canary, you get this huge file. When you're in native Canary data storage, it's really efficient. So absent a hard drive crash or something like that, which we haven't had with any of the Canary systems, there's a large amount of historical data there. Having said that, on the oil and gas side of our controls and remote monitoring business, that's an application where the owners are really, really, really intent on redundant backups, and a lot of that it's geographically remote too. So we'll set up virtual servers and things like that to take care of that, and we can schedule it. We can look at bandwidth availability to work with it. There's a lot of tricks we can play there, but bottom line, the bullet item is if you need it, there's ways to do it. If you don't need it, it's an expense you can avoid too.
Yeah, I think I would definitely concur with that. It's project-specific, user-specific, and maybe a function of something like your grant requirements or your funding or other things. I think there is a lot of value in your historical data, but again, if it's onerous to the project to be transmitting that, maybe not needed. I think on our end, for the data management side of it, it's trying to reduce the cost of the data management aspect to make it more worthwhile. For instance, being able to analyze your historical data to find opportunities for optimization or other areas of cost savings in your system.
Thank you. I noticed we're starting to lose a few people, so I'll just make 2 or 3 quick announcements. If you can take time to fill out one of the blue evaluation forms of the session, that would be good to let us know what we did well and what we could improve on. We also have the continuing education credit form. If anyone needs that, I can sign their form. And then also for folks, we're going to have some speakers in here at 12:30. So if you get your meal at the restaurant over here, please bring it back over here to actually eat that so you can catch the speaker. And so we had some other questions here. Yes, Gordon.
Should I just do it in here? If you want. I'll go get my scooch a little bit.
So the question is, with the black box, how do we do data transmission? And it is by, I guess, quote unquote, hand. So it's designed where you can literally walk up to it with a USB drive, plug it in, and it'll upload the data from that data sets that you need. And then for that thumb drive or hard drive to be shipped or transmitted to ASAP. And there's other things about the black box. It's triple redundant, and there's various backups to it. But that's really a potential solution for very remote communities with limited or poor internet connectivity that you can still collect and transmit high-resolution data.
Yeah. Question over here.
I see the data as a means to an end for each speaker's mentioned purposes and uses. I'm kind of curious about a benchmark objective use of data optimization. I'm curious, how do they understand the nature of data analysis so it's actually functionally used to optimize that lead us optimize curious if that's theoretical standard operating practice. It's a question of you got data.
Yeah, and I think part of it is you put the key word in your question, benchmarking. That's kind of the first thing we do is we'll look at the data and see how. Do we even think our instrumentation is working properly, and then what is our baseline? And it's also a good measuring point as you start installing these new systems and upgrades to be able to grade against that baseline. But first you can tell, does your baseline even make sense, or are there problems in the way you've got your instrumentation set up?
Yeah, I'd echo that. I guess couple examples. One is when I talked about the spilling on the water tank. That was one that was pretty obvious when you see it, right? Because you see what the levels are doing. So we didn't need any baseline for that, because you look at the data and you go, oh, I got it now. It's a way to look at a system without actually being there. I think the other ones, the differential pressure across the fuel filter or intake air filter, is one that it takes some more baseline data. So yeah, the good news is day one you start it up, you have no baseline data, but day 60 you get 60 days of baseline data, so it's never too early to start, kind of thing. There was something else too that
I'd add too, you should be cautious as soon as you start measuring something, you may see some anomalies. They may have been going on for years. When I was at Intel, we might do a new analytical technique and see something, and the temptation was to stop the production line because, hey, we see this defect, when you may have had that all along through the history of your process, and your product is still passing the quality and reliability. So you need to spend some time just understanding to what degree that signal is alarming or not. So as opposed to just immediately calling all hands on deck to fix a problem that may not actually be a problem.
Yeah, I guess, and the third point on mine too is you get what it gives you is it gives the operators, who are really the experts on any of these systems, it gives them another way of looking at stuff. So they've got a different perspective, and those guys see a whole lot more than we do. I mean, I could sit here all day and talk about the number of times we get a call from an operator and he says, this doesn't look right. What do you think about this? And we look at it from the SCADA side, from the data side, plus from some operating history we've got with other utilities. But man, those guys are the best guys in the world on their own systems.
We got time for one more question, and then we should wrap it up. Okay, well, thank you very much, folks, and enjoy lunch.